Hello, friends. Welcome to Science Talk. I am your host, Jim Massa. I want to, in this video, um, give a recap, review of the prior two videos I posted where I discuss ongoing methane research in the LabTev C. I'll start with the first one, the one I was the shorter of the two videos. And in that video, I was basically bringing you an update on Dr. Igor Semeletov's uh, research, him and his research team, and what they are doing in the LabTev C. What they are studying is basically what, in essence, biogenic sources of methane. Now, just as we have on terrestrial portions, for example, around the circumpolar north, Siberia especially, is that the permafrost is warming up due to the atmosphere warming up. This is causing the permafrost to thaw, and depending on where the location is, uh, the permafrost layer can be just a couple of meters all the way down to hundreds of meters. And as it thaws out, it allows for microbial action to work on the organic material. And as a result of the physiology of those microbes, methane gas is produced and released into the atmosphere. And those bacteria are typically called methanogens because they create methane. That process tends to be on a gradual scale, if you will. The release rate from the microbes is slow, but of course, when you take into account the entire region that this could be taking place, that is a significant contribution. But nevertheless, the rate of release is slow. We're seeing the same thing in shallow shelf areas of the ocean, such as the East Siberian Arctic Shelf, the Laptev Sea, the Kara Sea, Barents, and so forth. And so, what Igor is and his team are measuring is basically what is the methane amount, trying to get a handle on the rate of release. So they're looking at basically the microbial action. So since the source of methane is from bacterial action, a biological source, we call it biogenic as being the methane derivative. And that's what he's looking at. And he's staying in basically, the close to shore, the shelf region, and taking his measurements, doing his transects, and so forth. And he's now getting some very good quantifiable data, which will then help us understand the potential for how much is there and how much could be released, and not only that, the rate at which is being released. You've heard me discuss before that what keeps scientists who study such matters up at night is trying to get a handle on how much methane is in the ground and at what rate will that methane be released. As I just mentioned a few moments ago, biogenic sources tend to be a slow rate of release, but nevertheless, when you sum up the region, the area involved, it is significant. And just like, with the warming air, we have the oceans are warming, and that warming ocean is helping to thaw out the substrate and allow the hydrates, the clathrates, to thaw out, which then allows the bacterial action to take place. Now, the second study that the second video that I did where I discussed the study, what they were looking at, first of all, they were in a different region. They were further away from shore. They were basically at what's called the shelf break. Now, what does that mean? When you look at the profile of an ocean, you start from the shoreline, you're moving out, it's getting deeper and deeper, but at a gradual rate. That's called the continental shelf. And then at some point, the shelf suddenly steepens as far as its slope, and it takes a very sharp dive to deeper depths. That's called the continental slope. And where it transitions from the shelf to the slope is oftentimes referred to as the shelf break. So it gets noticeably steeper if you were to follow the terrain. That's where this study was doing its research. They were at the shelf break where it gets much deeper, much more quickly. And what they were finding was that there is this huge amounts of methane gas in pockets trapped in the rocks that are now, thanks to the oceans being warmer, that they were being released. Now, here's the problem and what they're trying to ascertain. And you recall in that study, they were looking at del C13, del C14, del deuterium as the isotopic signatures to help trace the source and the location of where the methane is coming from. Now, if the gas that is trapped leaks out more like it seeps into the water at very low amounts and a very slow, low rate, then it is very conceivable that that methane gas, will be able to go into solution in the water. Now, if it does that, if it goes into solution, then the methane will be subjected to physical activities, the physical mechanisms, the where the gyres are flowing, the currents are flowing, and the Ekman pumping, upwelling, downwelling, and so forth. Right? So the methane will be in solution, subjected to the physical activities, the physical actions of what the surrounding waters are doing. What they were finding, however, was that in addition to some slow seepage, and thus methane going into solution, what they're finding were explosive amounts of methane just being released. Literally like little bombs going off. Because there's so much of this methane that is being released at once in large amounts, a lot of it does not go into solution in the water. Instead, it just blasts right on through the entire water column up to the surface, where it then goes directly into the atmosphere. That's what they were finding. So, halocline, pycnocline, doesn't matter. That gas will just blow right through all of that and go right up to the surface. That's what they're finding. This is what they're trying to get a handle on. Because this is not the result of bacterial, biological, microbial action, they're referring to this source of methane, thermogenic. Thermo, of course, meaning heat, genic, the genesis. So basically, what it's saying that this source of methane has its basis in heat. What's that heat? It is, of course, the warming oceans. The oceans now hold a lot of energy. When I did my ocean heat content video, I reported to you that at the time that the oceans have pretty much about over 200 zettajoules of energy that have been absorbed. 93% of greenhouse gas emissions over the last 50 years. That number is now up to 226 zettajoules. So I did that video, 4 months ago or so, plus or minus. maybe a little longer. So we basically added another 10% of heat energy in that interval. That in of itself should be alarming. So you have this warm water that's basically thawing, melting the substrate, and a lot of times you have like an icy cap, covering the substrate. The warming waters melts that cap, which is like basically holds the gas trap. You remove that icy cap, and suddenly the methane has a place to go. And you might recall the authors were using the terms chimneys, because basically you just have this literally a chimney-like situation. You remove the impediment, and boom, you just have these sudden releases, these explosive releases of methane. That's what they were describing, and that's what I tried to explain in that video. This is of concern because this is a new source of methane, and we need to find out what's the potential, how much is there. We know there's going to be a fast release rate, but how much is there that potentially can be released? So that is basically, so think of it now that we have biogenic source on one hand, thermogenic source on the other hand for methane. One tends to be more of a slow process, the biogenic. The other tends to be more of the explosive nature, thermogenic. The thermogenic source will put a lot of methane into the atmosphere versus the biogenic putting methane at a slower rate. But when you take the accumulation of the biogenic processes on the shelf as well as on the terrestrial side, that is a significant source. So what we don't know now is, and this study is leading the way on it, we don't know how widespread these thermogenic sources are. What's the potential? And of course, what is the potential amount of methane that is there? From what I'm seeing, the indications are that there is a significant amount. I shared with you some of the estimates, which of course have potential for error, that anywhere from 14 to 100 gigatons of methane is possibly locked away in the substrate. So warming air thaws out the terrestrial permafrost. Warming water, oceanic waters, thaws out the subsea substrate, activating both biogenic and thermogenic sources of methane. So that's basically what those two videos were trying to explain. Bring you up to I brought with you the work of Igor. Before, it's kind of an update on what he's been up to, and you bring in this thermogenic source, and when Natalia, Dr. Natalia Shakova and Igor were warning us of the great potential there, they were ridiculed. I think those folks who were ridiculing them, they should be apologizing to them. Natalia and Igor are excellent scientists, good people. I know them, and they do very good work. Another thing I want to mention, not quite related to this, but it sort of is in a peripheral manner. I did a recent video examining a very interesting hypothesis that has been put forth recently, and that is was the Arctic Ocean once a big freshwater lake. And basically, using some analysis that these researchers did, and it's in the video. If you haven't seen it, please go check it out. And that during the ice ages, when sea levels are lower, significantly lower, the Arctic Ocean became an isolated basin. Basically, Beringia emerges, so you shut it off on the Pacific side, and the sea levels drop sufficiently that the Lomonosov Ridge literally shuts off on the Atlantic side. So you trap in this containment. And with all the freshwater, riverine input, precipitation, snow, etc., basically becomes freshwater. Then as the sea levels start to rise again, you then have at first the inundation from the Atlantic side. So now you have this Atlantic water, which has is saline. So you're bringing in this more dense water. The saline water spills over the Lomonosov Ridge, displacing the fresh water. Where that fresh water goes depends on the situation, but typically maybe through the Canadian archipelago into the North Atlantic, where you now introduce fresh water into the North Atlantic. So you have this dense water spilling over Lomonosov Ridge, displacing water, sinking to the bottom. Why is that important? Because we're seeing this today. Now, granted, Lomonosov Ridge is submerged, but we're seeing what? The warmer, saltier water from the Atlantic and from the Pacific as well. We're seeing that displacing the Arctic water, right? The water is more dense, it sinks, it pushes out the less saline Arctic Ocean water. Process called Atlantification. Now, I just did a video that the Arctic sea ice is succumbing to Atlantification. I did one about a year or so ago about the Barents Sea becoming Atlantified. We're now starting to see Atlantification all throughout the Arctic Ocean region, shelf and deeper areas as well. Eurasian, Canadian basin, Amerasian basin, etc. So, as I said to you before, if you want to, get a handle on what's likely to happen in the future, look to the past. There are lessons to learn from the past. So, that video, you might think, oh, this is kind of an interesting thing, but no, it has. There are lessons in there for some of the processes that are taking place today, and we can kind of apply them and learn from them. But the Arctic Ocean is changing. We're seeing the physical characteristics change. So I just wanted to bring you those updates and kind of give a recap on the two major sources, oceanic sources of methane, biogenic and thermogenic, and that there is great potential for high amounts of methane to be released. If it's biogenic in the oceans, it has a tendency to stay in solution, so it'll take a longer time for it to make its way to the surface and diffuse from the ocean to the atmosphere. But the thermogenic seems to be blasting its way straight into the atmosphere. Either way, they will eventually get to the atmosphere, slowly or quickly, increasing the levels of methane, increasing basically the CO2 equivalent levels. And people say, well, methane doesn't last long in the atmosphere. No, it just happens to oxidize down to CO2, and the CO2 has long-lasting effect. So the effects are going to be felt. So, people are still talking about, well, we got to net zero emissions, we can still prevent 2 degrees C warming. Saying 2C, and they've kind of conceded 1.5. But, so they're saying all this. Well, they're still forgetting the fact that that's only, what we're feeling now is only 7% of the emissions people have put into the atmosphere. What we're experiencing today is due to the CO2 level or CO2 equivalent levels of 10, 15 years ago. We're not going to know the effects of today's CO2 equivalent level for another 10 to 15 years. It's going to be a hell of a lot warmer. With the methane and the CO2 and the nitrous oxide. But the other 93% is in the ocean, and that great source of heat energy is going to diffuse into the atmosphere. Even if all of it does not diffuse in the atmosphere, a significant amount of it will, which will increase temperatures further by a very noticeable amount of at least 3 or 4 C, from the estimates that I've seen. So once again, people, especially atmospheric scientists, they ignore the oceans. And I think they do so because we breathe air. We don't live in the ocean. But, the planet is not Earth. It should be called Oceanus. There's so much heat energy in the oceans that it will diffuse, and it is diffusing now. We're seeing it now. It diffuses upwards, melts the sea ice from below, and if there is no sea ice, it just continues on into the atmosphere, adding to the ever-warming situation. That's all part of Arctic amplification. So, do not neglect, do not dismiss the role of the oceans. That's why I am of the opinion we can get to net zero. It won't mean diddly squat because of all that thermal inertia in the oceans now. And that is making its way into that oceanic heat is making its way into the Arctic Ocean and drastically changing what's going on. I'll give you an example. This is the month of October is coming to an end. Temperatures here in the Fairbanks area have been in the 20s. It used to be in October would be in the teens, maybe single digits, sometimes below zero on the Fahrenheit scale. Now it's warmer. Why? Because the Arctic Ocean hasn't frozen over yet like it would typically do by now. Although this year is kind of interesting. We're seeing ice in the Chukchi and Beaufort a little sooner. So it's not near the bottom of, amounts and the time for freeze up and so on. And that's because of what the Arctic Dipole is doing. There's some interesting things going on where Alaska's a little on the cooler side and everywhere else in the circumpolar north is on the warmer side. So, well, lucky us. But there's still more open water, so that latent heat, that heat energy is diffusing to the atmosphere and it's making things a little warmer for us. I expect that once the ice starts really freezing up, come November, temperatures will cool down to cooler situations, to what may be typical. But that's just an example. In fact, Alaska, the month of October is the month that we see the warmest departure from average temperatures. And that's because the Arctic Ocean is remaining open. You've heard me say it before, I'll say it again. What happens in the Arctic does not stay in the Arctic. So, there you have it. Biogenic, thermogenic sources of methane, all which spells trouble because this will create positive feedback loops that will, of course, release more methane, further warming the situation, adding to Arctic amplification. And all I can say is stay tuned. Thank you for your time.